Hello, Algebra 2 learners. This is for exponential and logarithmic functions. Specifically, we're going to be focusing on the fact that exponential and logarithmic functions are inverses of one another, and we're going to be looking at how to graph logarithmic functions. As you'll notice here, we have a graph in blue, y equals log x, and in red, y equals 10. And we learned in section 3 that these are inverses of one another, that y equals log x is the common logarithm. So, as you remember, there's an understood base 10 here. And these are inverses. And again, we call this the common logarithm. Right, and you can remember, don't forget, if you look on your calculator, you have the log button, and right above it as the second function, you have y equals 10 to the x. And as you'll see similarly later in this video, you'll remember that we also have y equals natural log x, which is the natural log. And we know that its inverse is, and think about it before I tell you, y equals e to the x. We had a question like that on the quiz that you did on quizzes on 6-3, and some of you made mistakes on that, weren't clear what the inverses were in terms of natural log. Okay. You'll notice here are some key features of the functions. Now, not only do I want to talk about the content here, I want to also talk about notation, because one of the things you'll notice is that when we mention, say, the domain here, it's written in set notation, which includes an inequality notation within it. And of course, you're used to interval notation, for example, 0 to infinity here, and for all real numbers, negative infinity to infinity, right? However, when you're doing your Pearson Realize assignment, they tend to use the notation that you see printed here. So I want you to keep that in mind, and so you understand the relationship between what we're used to and what the textbook uses. Also, something you'll notice is that in your Pearson Realize assignment, when they request an x-intercept or a y-intercept, generally you're just going to type in the number, like in this case, x-intercept 1. So you just type the 1 in. Unless, I believe, in one case on the assignment that you're going to be doing for 6-4, they do request the intercept as a coordinate, in which case you write it as a coordinate. As, for example, in this case, it would be 1, 0. Or in this case, for the y-intercept, 0, 1. Okay? But you'll notice the fact that we have these functions log x and y equals 10 to the x inverses of one another. Notice how the domain and range also switch. Remember, x and y switch for each coordinate on the graphs, but also the domain and range are going to switch because domain are the set of x values and range is the set of y values. So as you'll notice here, of course, as we knew from the past, earlier when we were before the break in school, we knew that the domain of exponential functions was all real numbers, and the range was 0 to infinity, and as you can see, that switches here. So when you're looking at log functions, reversing, just like you're reversing x and y's. And similarly, remember with exponential functions, the y-intercept for the parent functions was 0, 1. And of course, what's going to happen here is going to switch that so the parent function for logs is going to have an exponent 0, which is y values. And as you remember, when we graphed the horizontal asymptote, the x-axis of y equals 0 for the parents, and here we're going to have a vertical asymptote at x equals 0, the y-axis. And then you'll also notice that the end behavior switches. So remember, for just a general exponential growth function, we had as x approaches infinity, y approaches infinity. We didn't focus on, I didn't make you write the end behavior at that point as x approaches negative infinity. But as you notice, if you look at the x approaches negative infinity here, as x approaches negative infinity, y approaches 0, and that also switches here. As x approaches 0, y approaches negative. When we look at the exponential and logarithmic functions, we want to be able to graph them. So we want to look at the parent tables. So let's just sort of review what we already knew about exponential functions. So for the parent exponential function, we know that we have y equals b to the x, and we have an infinite number of parent exponential functions because as we change the base, we have a different exponential function. And remember, I always had you graph using 3 coordinates to make it simple. We said when x was -1, b to the -1 gave us 1 over b. When x was 0, b to the 0 gave us 1. And then when x was 1, b to the first power gave us b. We always had -1, 1 over b, 0, 1, 1b. Okay? And so you can imagine when we go to the logarithmic function, which is an inverse, we just reverse x and y. So the parent table that we're going to use for the log function is just the reverse x and y of what we used for exponentials. We have y equals log base b of x. And again, we have an infinite number of log functions here depending on what the base is. And we just switch the x and y's. So instead of having -1, 1 over b, 0, 1, 1b, we'll have 1 over b, -1, 1, 0, b, 1. Okay. Also, when we're graphing, we might recall that when we're graphing transformations of exponential functions, we use this formula, y equals a times b to the x minus h plus k. And we know that h allows us to translate left and right, k up and down, a deals with vertical stretches or shrinks, and also reflections over the x-axis. Well, of course, the same is going to be true over here for parent log functions. So I'll do the same sort of formula over here. So when we want to do transformations for logs, we're just going to say y equals a times log base b. And in parentheses, we'll say x minus h plus k. Okay? Now, it's very important for you to focus on what's in parentheses here and what's out of parentheses here. And we'll see that a lot later on when we're graphing and when we're calculating inverses. We want to be very careful. And I'll be referring to what's inside parentheses as the argument of the log functions. It's the expression that we're taking the log of. So when I talk about log base b of x minus h, that x minus h I'll refer to as the argument. Okay. And you want to focus on what is in the argument and what is not. So we're going to start graphing the exponential equation and its inverse. And we had an example up here, of course, with a common logarithm. And one thing you'll notice up here with the common logarithm is, just as is true of any other inverse function, you're always going to be looking at the graphs reflecting over the line y equals x. Okay? So they're always going to be symmetric over this line because they're inverses. All right, and we'll notice the exact same thing when we graph in other bases. Okay, so let's look at the exponential equation y equals 2 to the x. Okay, as you know, this is y equals b to the x, and because b here is greater than 1, we know that we're dealing with exponential growth. Okay, and you probably remember, and you'd be able to see this also when we graph it, that the domain is going to be all real numbers. We were looking at this above because basically the domain range, the y-intercept, the asymptote, and the end behavior are going to be exactly the same as what we had up here for y is equal to 10 to the x. Okay, that's going to be true of any parent exponential function that we haven't translated left, right, up, or down. Okay. So the range, you could just copy this right from above, but we can also check it when we graph, is 0 to infinity. The y-intercept is 0, 1. The asymptote is going to be a horizontal asymptote, and it's going to be y equals 0, which is the x-axis. And we'll fill in the end behavior because I want you to be able to see that from the graph. Obviously, we already know the answer. It's right above for y equals 10 to the x, but let's just look at the graph and kind of see how we can come up with that end behavior from that. Okay. So if we make this table, we've got x, y, and we're going to do negative 1, 1 over b, but b, of course, here is equal to 2, right? So negative 1, 1 over b, see the 1 over b is going to be 1 over 2. 0, 1, 1, 2. Okay. And because of the numbers I've got here, I can go ahead and I can scale this graph counting by ones. And so I've got negative 1, 1 half, 0, 1, 1, 2. And go ahead and make that curve. Okay. And we're going to observe here, we have that horizontal asymptote that we talked about. And, you know, we don't have to dash it because it's an axis. So I'll just go ahead and highlight it here. So we have a horizontal asymptote at y equals 0 for the exponential function. Okay. Now, its inverse, as we hopefully remember from section 6.3, is going to be the log function with the same base. And so the inverse is going to be y is equal to log base 2 of x. Okay? And now think about, obviously, how we're going to come up with the table for the log equation. Okay? Well, there's two ways we can do it. Okay? One way is obviously we know that these are inverses of each other, so I could just reverse x and y, and I get the correct table. Also, I can go back and remember, because in certain cases, we're going to be just starting with a log equation. We're not going to have the exponential in front of us. We can just look at our parent log function table and use that. Okay? So either way, we'll end up with this table here. And because it's right in front of me, I'm just going to reverse the x, y values here. So I'll have 1 half, negative 1, 1, 0, 2, 1. And I will graph that in green. So I've got 1 half, negative 1, 1, 0, 2, 1. Okay. Now, before I graph this, I want to make sure I'm aware of where my asymptote is. Okay. Now, I want you to remember from up here, we talked about that the log function, y equals log x, is 10, and it doesn't matter if it's base 10 or base 2, which is what we're working with now, the asymptote is going to be vertical at x equals 0. Okay. So we can see here that we're going to have a vertical asymptote at x equals 0. Which makes sense, right? Because we're reversing x and y. So if the exponential function had a horizontal asymptote at y equals 0, the logarithmic function is going to have a vertical asymptote at x equals 0. Okay, and it's very important that you, if it's an axis, highlight it or make note of it. And if it's not an asymptote, or excuse me, if it's not an axis, then you definitely want to dash it before you draw your curve so you don't cross over that asymptote. Okay? And so you can see here, as we would expect, I can go ahead and I can graph the line y equals x, dash that right in here, and you can see those graphs are symmetric over that line. Y equals x. Okay, so let's fill in this domain and range here. Now, when I fill in the domain and range, you can notice I can just reverse the domain and range from the exponential. And again, it's the exact same domain and range that we had for y equals log x, because again, these parent log and exponential functions are going to have the same domain and range regardless of the base. Okay. Same domain and range, same x-intercept, same y-intercept, same asymptote, same end behavior regardless of the base, as long as you haven't transformed the graph. So I'm just going to reverse the domain and range from exponential, and I'll get 0 to infinity here, negative infinity, infinity. The x-intercept is 1, 0. The asymptote is vertical asymptote at x equals 0. And we didn't fill in the end behavior here and the end behavior here, so let's go ahead and fill those in now. So as you'll notice here, let's just look at this so we can see it without cheating and looking above at what we had for y equals 10 to the x and y equals log x. We look at y equals 2 to the x here. You can see as x approaches negative infinity, y is approaching 0. It's getting closer and closer to that asymptote. Okay, and as x approaches infinity, y approaches infinity. Okay, when we were graphing exponential functions earlier in the chapter before the break, I just had you focus on positive infinity. But now I'd like to work on both directions because it helps you see it when you're kind of comparing it to a log function. Okay, and so now you can look at the green line for the log function. Okay, as x approaches, now look at where x is approaching. It's getting closer and closer to its asymptote, x equals 0. So as x approaches 0, y approaches negative infinity. And you can see, look, compare. See how they reverse? Negative infinity, 0, 0, negative infinity. Okay? And for the other direction, as x approaches infinity, y approaches infinity. And as you can see, that makes sense because you see, if I flip-flop these, I'm still going to get the same thing, infinity and infinity. Okay? All right, so we're going to move on now to a few more examples. And after these next two examples, I will pause the video for a moment to kind of encourage you to pause as well, and then I'll continue. I did decide to make one video, as I did last time, but this time I'm going to pause myself in the middle as well to definitely encourage you to pause. And that way I can take a break, and you can take a break, and you can kind of go back, absorb what we've learned already, and then continue from there. So I'm going to take 2 pauses for this lesson. So let's look at the exponential equation y is equal to e to the x. Remember that what you're looking at here is the natural base. And the logarithmic equation is going to be, of course, the inverse of that, which is the natural log. Put that in green. I'm going to try to be consistent, putting exponential in pink and log in green. So this is natural log. Okay? And so this is going to be y equals natural log of x. And remember how we get that, right? You want to note this is the same as y equals log base e of x. It's just typically we write natural log. Remember, you can see those this natural log button on your calculator, and this should be at the same level of natural log, should be right here. And you'll notice on your calculator, you have that natural log button, and e to the x is the second function for it. Okay. So let's go ahead and make the tables, and we'll go back and fill in this information, because again, this information that we see over here is going to be identical to what you just had for y equals 2 to the x and y equals log base 2 of x, because these parent exponential and log functions are going to have the same domain, range, y-intercept, and behavior. So you can literally copy that over from what you saw before, and you can even fill it in maybe before I do to test yourself and make sure you can do it after we've drawn the graph. So I'm going to draw the graph first and then see if you can fill this information in. Maybe you can even pause the video when I don't to kind of get, test yourself and make sure that you fill that information in on your own. Okay. So let's go ahead and make the parent table for y equals e to the x. So we have, again, -1, 1 over b, but b is base e. So this is 1 over e. And by the way, think about for a moment, you don't actually see the number here, but think about what base e is approximately. And then think to yourself, is this growth or is this decay? Okay, so in other words, what should my graph look like? So hopefully you've thought about that for a moment, and you know that E is approximately 2.718, therefore we have exponential growth because that's the value of B. Okay, so you have -1, 1 over B, 0, 1, 1, B, which is E. Okay. Now, E, we just said, is 2.718. So when you graph this, you're just going to approximate on the graph about where 2.7 is. I went ahead and, before we started, divided 1 divided by E to save us some time. If you do that on your calculator, you can verify it. Out to 3 decimal places, it's about 0.368. Okay. So if I want to go ahead and graph that, I have -1. About a third, -1 and about a third, 0, 1, 1, 2.7, about here. Okay. Now, again, before you graph this, think about what your asymptote is. You might want to go ahead and fill that in now. You want to remember that your asymptote is going to be the x-axis, right? It's a horizontal asymptote at y equals 0. So keep that in mind. Don't go over that line when you make that graph. Okay. And here's that horizontal asymptote. Okay. Horizontal asymptote at y equals 0. So to graph the logarithmic equation, again, I can do it from scratch using the parent log function, because remember, exponential functions, log functions, each have their own separate parent. But if I already have one, I can always just reverse the x and y's to get the other, right? So you can see, I'm going to take x and y here. I can say 1 over e, -1, 1, 0, e1. Okay, so compare that. Noticing y over. And so we've got 0.368. Okay. So 368 -1, about a third, -1, 0, and then 2.718, and then 1. And remember, what's our asymptote? We have a vertical asymptote at x equals 0. Okay, so draw that vertical asymptote in, and vertical asymptote, x equals 0. So that way when we draw our line, we don't go over that asymptote. Okay? And remember, there's that line y equals x that we are always going to be symmetric over. Okay? So let's fill in the domain, the range, the x-intercept, and the end behavior. Okay? So as far as for, if we just do it for exponential functions, we can literally just reverse the values for the log functions, right? So for the domain of the exponential functions, as we knew from the past, all real numbers, range goes from 0 to infinity. The y-intercept, you can see, is at 0, 1. Okay? And so let's flip that around. So we have our domain of the log function. As you can see here, the domain is starting at 0, going to infinity. Of course, it's not touching 0, and that's why we have parentheses. So we have the domain, 0 to infinity. So I'll put that in green. So domain, 0 to infinity. Okay. The range is going to be all real numbers. And you can verify that from the graph. Just look at the graph. X-intercept, just reverse this. We have 1, 0. Okay. Let's look at the end behavior. Okay, again, this is exactly what we did before. So I'm hoping some of you have already filled this in or paused it and filled it in, because I had said you can just literally copy over from what we just did to y equals 2 to the x, right? So the end behavior, as x approaches negative infinity, y is getting closer to the asymptote, y approaches 0, right? And as x approaches infinity, y approaches infinity. Okay, and let's just switch that around here, right? So here, as x approaches 0, y is going to approach negative infinity. Again, see that switch? Okay, and as x approaches infinity, y approaches infinity. Okay. All right, one more example, and then I'd like you to definitely pause and go back and review what you've learned so far before you continue. Okay. So finally here we get to one that we haven't looked at yet today, and that is a decay function, right? And how do we know it's exponential decay? Think about that for a moment. As you'll see here, we've got y equals b to the x, and as you can see, b here is going to be less than 1. Of course, it's always positive, right? So b is always positive. It's always greater than 0, right? But it's less than 1. It's between 0 and 1 at 1/2. Therefore, we have decay, right? So again, we can fill these in after. We'll make the table. And we're going to do -1, 1 over b. Well, remember, if b here, b is equal to 1/2, 1 over b is its reciprocal, which would be 2. Okay, 0, 1, 1b, which is 1/2. Okay. Now, I'm going to go ahead and I'll fill in the logarithmic equation, and we'll graph both. So the logarithmic equation here, hopefully you can see, we know that we keep the same base, and we just say y equals log base 1/2 of x. Okay, remember, you can have fractional bases for logarithmic functions. That's perfectly acceptable. Okay, so we're going to now just take the table that we had for the exponential function and reverse it, or just remember, you can always go back. So I want to remind you what we looked at here, the parent log function, 1 over b -1, 1, 0, b1. Okay, but in this case, if we already have the exponential, I'm just going to reverse these values. So we have 2, -1, 1, 0, 1/2, 1. Okay. And remember what the asymptotes are. So keep that in mind. It's going to be the same as what we had before. So when you graph this, make sure you're aware of those asymptotes. So for the exponential, we have a horizontal asymptote at y equals 0. And for the logarithmic, we have a vertical asymptote at x equals 0. Okay. So we've got -1, 2, 0, 1, 1, 1. Okay, and with that horizontal asymptote at y equals 0, right here, and I'll just go ahead and I'll fill in that color. Okay, and I'll do the same now for the logarithmic, the inverse. Okay, so we've got 2, -1, 1, 0, 1, and be mindful of that vertical asymptote at x equals 0 when you draw this line. So there's that vertical asymptote at x equals 0. And we'll go ahead and we'll draw this line. And there we go. And we'll just draw that y equals x line to remind ourselves, make sure it's a good way of checking your graphs, because you know that these graphs always have to be symmetric. They have to be mirror images of each other over that line y equals x. And sure enough, if you look carefully at these lines that I've drawn, they are. And so that's a good check for yourself. Okay, so we'll just fill in these domain, range, y-intercept, and end behavior for both, and then we'll take a pause, and I'd like you to go back, review what you've done in this first section of the notes, and then we'll continue from there. Okay, so as you can see, if you look in the pink, and also based on what we've already done repeatedly for these parent exponential functions, the domain, as you know, is all real numbers, which means, of course, that for the logarithmic function, the range is all real numbers, right? And the range here goes from right above that horizontal asymptote up to infinity. And so we know the range is 0 to infinity, which means that the domain of the log function is from 0 to infinity, right? The y-intercept here, of course, is 0, 1, which means that the x-intercept here is going to be 1, 0. And then finally, we'll fill in the end behavior, and then we'll take a break. So as you can just check here, as x approaches negative infinity, y approaches infinity. Now notice, this is because this is decay, this is going to change a little bit as far as compared to what we were looking at with growth, right? So as x approaches negative infinity, y is approaching infinity. And we'll notice here, as x approaches infinity, y is approaching 0. So as x is getting really big, y is getting closer and closer to the horizontal asymptote, y equals 0. Okay. And so let's just do some switching around for the log function. Okay. So notice, as x approaches negative infinity, or actually as x approaches 0, so look closely there, x is getting closer and closer and closer and closer and closer to the vertical asymptote at x equals 0. So as x approaches 0, y is approaching infinity. Okay. And as x approaches infinity, as x is getting really, really large, right? As we move to the right on this graph, x is getting really, really large, but simultaneously, y is getting really, really small. Y is approaching negative infinity. And let's look at that here. Notice, okay, let's do some reversing. You notice as x approaches infinity, y approaches 0. Compare that here. As x approaches 0, y approaches infinity. You have these reversed. And notice here, as x approaches negative infinity, y approaches infinity. As x approaches infinity, y approaches negative infinity. You can see those reverse because we're dealing with inverses. Okay. So take a break. I'm going to pause the video here and then I'll continue so that you can absorb what you're doing. Okay, everyone, I hope you've taken a little break and looked over the first part of the notes. We're going to continue now by graphing transformations of logarithmic functions. And basically, we're going to do a very similar process to what we did with exponential functions, where we're going to take the parent function and then look at whatever transformations we have and adjust the table accordingly. Okay, so let's remember what we talked about on the first part of the video. Remember that for if we want to transform parent log functions, we can use this equation. Okay, and I said to be sure to focus on what's inside parentheses as opposed to what is outside parentheses, because the expression inside parentheses will have to do with a shift left or right, whereas the number outside parentheses has to do with a shift up or down. And that shift left or right is what is going to change the vertical asymptote. Okay, so remember when we were dealing with graphing exponential functions before spring break, we always had a horizontal asymptote at y equals 0 unless we shifted up or down, unless we changed k. So now, since with log functions we're dealing with vertical asymptotes, what we're going to be focusing on is shifts left or right that are going to change the vertical asymptote from the y-axis, which is x equals 0. Okay. Also, notice the parent table, which is going to just simply change based on the value of b that we have. So this is the parent table that we're going to be used. So I'm going to go ahead and copy that over right into the question that we're dealing with now. Okay. All right, so we've got y equals log base 2 of x plus 3. So keep in mind that transformation equation that we were just looking at. We've got y is equal to a times log base b of x minus h plus k. And so what you'll notice here is that there is no vertical shift up or down. We just have a change in the value of h. And we can see, since it's the opposite of x minus h, we have x plus 3 here, then we know that h is equal to negative 3. And with h is equal to negative 3, that tells us we're going to have a shift left 3. Okay, and as I was just talking about, that also tells us that our vertical asymptote is going to change. The vertical asymptote now is always going to be based on the value of h. It's x equals h. So in this case, it's x equals negative 3. And so we can copy that right down here in our asymptote. Vertical asymptote is going to be x equals negative 3. Okay. And something that we can always fill in here also is that we can always keep in mind that the range of a logarithmic function is always going to be all real numbers, just like the domain of an exponential function is always all real numbers, okay? And the domain is going to depend on the vertical asymptote. So instead of going from 0 to infinity, now because we have that vertical asymptote at x equals negative 3, the domain is going to go from negative 3 to infinity. And again, after you graph that, you could verify that and you could see that, okay? And we'll fill in the x-intercept and the end behavior after we've done the graphing, okay? So let's take that parent table that we were talking about, and that parent is here. So we have 1 over b, negative 1, 1, 0, b, 1, okay? And so in this particular case here, we have got, this is going to be y equals log base 2 of x. So this is y equals log base 2 of x. Squeezing that in there. But that's y equals log base 2 of x. And just fill in the base 2, so it's 1/2 negative 1, 1, 0, 2, 1. Okay? And we'll also go, and we'll now change this because we're shifting left 3. And I guess I'll put that actual graph that we're going to do in pink. So we've got, we're going to shift left 3, which means, as you know, we're going to subtract 3 from the x values of the parent. Okay. So if we subtract 3, 1/2 minus 3 is negative 2.5. 1 minus 3 is negative 2, and 2 minus 3 is negative 1. And the y values stay the same because we're not shifting up or down, and we're not vertically stretching or shrinking, and we're not reflecting. Okay? So I'm just going to leave that at negative 1, 0, 1. So let's go ahead and keep in mind that vertical asymptote is at x equals negative 3. And so I'm going to dash that in, or actually in this case, yes, we'll dash that in because it's not an axis. So I'll dash in that vertical asymptote at x equals negative 3. And I guess I'll do that in pink. Okay, so there's the vertical asymptote at x equals negative 3. And we'll go ahead and graph this. We've got negative 2.5, negative 1, negative 2, 0, negative 1, 1. And we'll use that vertical asymptote and we'll draw the graph. Okay? And if you want, you can also highlight this just so that you have it. You can really see that asymptote there. Okay? Otherwise, just dash it in. Now, what I want to do here, just to emphasize, and I'm going to have you do the same thing. You're going to be doing, as part of your assignments, in addition to the Pearson assignment, you're going to be doing a graphing worksheet. And on that graphing worksheet, I'm going to have you graph the log function, but I'm going to also have you dash in the inverse, which is the exponential function. Okay? So that inverse, the exponential function, if you recognize, of course, we can just reverse the xy values. So if we want to graph the inverse, we can just graph at negative 1, negative 2.5, negative 1, negative 2.5, 0, negative 2, and 1, negative 1. Okay, and also keep in mind that as far as figuring out where that asymptote is, if we have a vertical asymptote at x equals negative 3 for the log function, for the exponential function, we're going to have a horizontal asymptote at y equals negative 3 because x and y simply reverse. And so I'm going to go ahead and I'll dash that in here, but I'll also highlight it. So here's that horizontal asymptote at y equals negative 3, okay? And remember, I got this by simply, in fact, I'm gonna just, I'll wipe that out so we just have it dashed in here, because that's all you have to do. You can just dash in the exponential function, okay? So this is the inverse graph. This is the horizontal asymptote is for the inverse, which is the exponential function, and that is dash. So dash the inverse, which is the exponential function, and that's like what I'd like you to do on your graphing assignment as well, okay? And you can see there's that y equals x line again, because they are inverses of one another. So we can go ahead and we can dash that y equals x line, just like before. So here's y equals x. Okay. So as you'll notice here, if you're looking at the graph, you can see what the x-intercept is just from the table. And you can also see it from your graph that the x-intercept is going to be at -2, 0. In a moment, however, we're also going to verify that algebraically because I'd like you to be able to do that. I'd like you to be able to take a logarithmic equation and be able to find the x-intercept from it without even having to make the table or graph it. And we're going to see how to do that momentarily. So we'll verify it algebraically. The end behavior we can see here as x is approaching -3, y is approaching -infinity, right? So as x approaches -3, y is approaching -infinity. Let me make that just a little clearer here. So as x approaches -3, y is approaching -infinity. And as x approaches infinity, y is approaching infinity. Okay? And I notice I use different colors here, so let's just make sure we're all clear. I'm going to say C pink graph. Just so you understand that that's what that goes to, because that is the graph of the original equation that we're looking for. Okay? So let's talk about calculating the x-intercept algebraically. All right? So I'm just going to go onto the back of these notes just for a moment because I don't want to clutter this up. And if you printed back to back, you could just use some separate paper if you want. But I just want to verify it algebraically. Okay, so we're going to take this y equals log base 2 of x plus 3, and we're going to calculate the x-intercept and see that it comes out to -2, 0. Okay. So we're going to verify algebraically the x-intercept of y equals log base 2 of x plus 3. Okay, so as you all know from prior knowledge, we know to find an x-intercept, we let y equal 0. So let's go ahead and do that. 0 equals log base 2 of x plus 3. Okay, now to be able to solve for x, we're going to change to exponential form. Okay, so we're going to solve for x, which will be the x-intercept, by changing to exponential form. Okay. So what we'll do is notice the base here is 2. The log is equal to the exponent, right? So we're reviewing this from section 6.3. Here's the base. The log is equal to the exponent. So the base is 2. The exponent is 0. And the number that we were taking the log of is going to be isolated on the other side of the equation. Okay, so here's your base. Here's your exponent. The log is going to be the exponent, right? And so we can see here, if we end up doing the calculations, 2 to the 0 here is 1. 1 is equal to x plus 3, and if I subtract 3, sure enough, I get -2 is equal to x. And if you look at the table and you look at your graph, sure enough, we've got an x-intercept of -2, 0. So I wanted to show you that algebraically we can verify that. And there is a question in the Pearson assignment that does address calculating an x-intercept towards the end of the assignment. Okay. All right, so let's look at another transformation. You notice up here for this example 2a, we just had a horizontal shift left 3. So now looking carefully at example 2b, you can see with that 5, we're going to have a vertical stretch by a factor of 5. Okay, so when you're dealing with a vertical stretch by a factor of 5, then your asymptote is the same as the asymptote for log base 2 of x, okay? The only time your asymptote is going to change is if you have a shift left or right, okay? Shift up or down is not going to change it, and a stretch or shrink or reflection is not going to change it, okay? So we're going to be going back to that vertical asymptote at x equals 0 again, okay? So the vertical asymptote here is going to be at x is equal to 0, all right? And the range, remember, think for a moment what the range is always going to be for a logarithmic function, regardless of what we do and what transformations we make. That range is going to be all real numbers, unless you're, of course, in a real world, like a word problem situation. But for any of our graphs, the range is always going to be all real numbers, just like for exponential functions, that the domain is always going to be all real numbers. Okay, and the domain is going to depend on that asymptote. So the domain is going to go from 0 to infinity. And again, you can verify all this when you actually make your graph. Okay, the x-intercept is going to be, excuse me, at 1, 0, just like the parent function would be without the vertical stretch. Because again, that x-intercept is not going to change unless you have a translation. And the end behavior is going to be the same as what we had for log base 2 of x, but we'll go ahead and we'll graph it first, and then we'll look at trying to look at the graph and describe the end behavior from the graph, okay? So again, we're going to use that same parent format as we used in part A up here, 1 over b negative 1, 1, 0, b1. And this time, however, we're going to be just transforming it differently. So we're still in base 2, so we can still use y equals log base 2 of x. We can still use the same parent table that we used up here, okay? So that y equals log base 2 of x parent table that we just used in part A is going to apply here as well. So we've got 1/2 negative 1, 1, 0, 2, 1. Okay, only difference here, of course, is now we're going to vertically stretch by a factor of 5, so we're going to multiply the y value by 5. Otherwise, the x value is going to stay the same, right? So we'll have 1/2, 1, 2 stays the same, and we'll just take the negative 1 and we'll multiply it by 5, so we'll get negative 5. 0 times 5 is 0, 1 times 5 is 5. Okay, and then we will make the graph, keep being mindful of the asymptote, and we'll also dash the inverse as well. All right, so the asymptote is vertical asymptote at x equals 0. So I'm going to dash that in. And actually, it's at x equals 0, so I don't even really have to dash it. I could just highlight it, right? Because it's the y-axis, because there's no shift left or right here. So we have a vertical asymptote at x equals 0. And we've got 1/2 negative 5. So 1/2, 1, 2, 3, 4, 5. 1, 0, 2, 1, 2, 3, 4, 5. You can see that vertical stretch here. You see how the shape of that graph changes from what we've been seeing because of the vertical stretch. Okay? And so we've got that graph. Let's go ahead and fill in that end behavior now. We can see that as, looking at the left side, x is approaching 0, the vertical asymptote. So as x approaches 0, y is approaching negative infinity. And as x approaches infinity, y approaches infinity. Okay, and again, I'm going to put over here C pink. And you can keep that in mind. That's the graph that we're doing, okay? And so now I'm just gonna do the inverse. Remember that if the log has a vertical asymptote at x equals 0, then the inverse, the exponential function, is going to be a horizontal asymptote at y equals 0, right? So this is the inverse exponential function, okay? And we're going to dash that inverse. So again, take the coordinates of the log function and just reverse them. So instead of 1/2 -5, we're going to have -5 1/2. So 1, 2, 3, 4, 5, 1/2. Instead of 1, 0, we're going to have the y-intercept at 0, 1. And instead of 2, 5, we're going to have 5, 2. Okay. And I'm going to go ahead and I'm going to dash that in. Be mindful of the shape of the graph, because if you just connected those points, you might accidentally draw a straight line. And you know, that is not a linear equation, it's exponential. So make sure you continue that graph, even though I'm not making you draw more than 3 points, okay? So that is the dashed is the inverse, the exponential function, okay? And definitely keep this in mind when you're doing your worksheet, because you're going to be using the same process. You're going to graph the log in a solid line and then dash the inverse. Okay, so the last function that we're going to do before we take another break, we're going to do an equation where we have several transformations. We've got a vertical stretch by a factor of 4. We've got a shift right 3 and a shift down 4. Okay, so make a list of those. So we've got a vertical stretch by a factor of 4, a shift right 3 and down 4. Okay. So remember that you need to notice what the base is, okay? So I want to highlight that here for you. Pay attention. See, in A and B, the base was base 2. But in C, the base is base 4. And so that parent table is going to be based on log base 4 of x, not log base 2 of x, right? So keep that in mind when you're making your table. So I'm going to write y equals log base 4 of x. And so when I make that parent table, I'm going to still use the 1 over b negative 1, 1, 0, b1, but that b now is 4 instead of 2. So I'm going to do 1/4 negative 1, 1, 0, 4, 1. All right. Now there's going to be several calculations that I'm going to have to do to get to the graph that I want, because we've got 3 different transformations going on here. So you want to make sure that you process all of those, right? So we're shifting right 3. So of course we know that means we're going to add 3 to x, all right? So we're going to get 3 and 1/4, 4 and 7. And then for y, remember multiplication comes before subtraction. So we're first going to multiply by 4. We're going to multiply y by 4, and then we're going to subtract 4, right? Multiply y by 4, subtract 4. And so if I do that, for example, for negative 1, okay? Multiply negative 1 times 4, I get negative 4. Subtract 4, I get negative 8. 0 times 4 is 0, minus 4 is negative 4. 1 times 4 is 4, minus 4 is 0. Okay, so those are the values that I'm going to graph. Now, you don't necessarily have to fill in all of this yet, but again, keep in mind of what we already know. Negative infinity, infinity, okay? the x-intercept we can actually get right from the table there, 7, 0. But again, you could verify that algebraically. So you can try that on your own. I'll also do it for you at the end of before we finish the video. But the vertical asymptote is going to be based on the value of h. So we'll look at that in a moment. But meanwhile, the x-intercept here, 7, 0. Let's fill that in, okay? Now the vertical asymptote, again, is going to be based on the value of h. So we've got y is equal to a times log base b of x minus h plus k, okay? And so in this case, remember up here, when we were shifting left 3, h was -3, the vertical asymptote was at x equals -3, okay? Here, h lines right up in terms of sign, so we can see that h is +3. So the vertical asymptote is x equals h, so the vertical asymptote is going to be at x equals 3. Okay, and that's very important for you to be able to draw your graph accurately. You've got to put that vertical asymptote dashed in there. Okay, again, the domain changes because of that vertical asymptote, so we're going now from 3 to infinity, again with a parentheses, x is greater than 3. And again, let's look at the end behavior after we've done the graph. Okay. So again, I'm going to do the graph in pink, and then we'll do the inverse in black. So again, let's just say we'll see pink here. And that's going to be this function. I'm just trying to be consistent from what I did before. The asymptote is at x equals 3, okay? So now before I actually graph here, let's pay attention to some of the numbers we have here so we don't run into a problem. Pay attention to the fact that we've got 1, 2, 3, 4, 5, 6 intervals here, but I need to graph 7, 0. So I'm going to count by 2s. I'm going to scale my graph by 2s, okay? And many of you tend to get a little bit lazy when you're labeling your graph, okay? If you're not counting by 1s, don't just label certain axes. Please label all 4 axes, especially you're going to be dealing with at least 2 out of the 4 of them in this case. So 2, 4, 6, 8, and we'll do -2, -4, -6, -8, -2, -4, -6, -8. Okay, so graphing in that vertical asymptote at x equals 3. Here it is, the vertical asymptote at x equals 3. And now we can graph the points. So we've got 3 1/4, -8. Let's see, 3 1/4, -8. So just a little bit to the right of that vertical asymptote, go down to -8, and there's your point. 4, -4, and 7, 0. Okay? Graph that line, make sure you approach that asymptote, but don't go over it. There's your approximate curve. And then again, to get the inverse, just reverse the xy values, okay? So make sure you're realizing that you're just reversing the xy values, and that's how we get the exponential function. So I'm going to graph the exponential function. I'm going to dash it. Also keep in mind that asymptote. So the asymptote is going to be at y is equal to 3 because the vertical asymptote was at x equals 3. Okay, so here's that. Y equals 3 is the vertical asymptote. The horizontal asymptote. We have a horizontal asymptote at y equals 3, and that's for the inverse exponential function. Okay. And let's just reverse the xy values. So we have -8, 3 1/4. So -8, 3 1/4, just a little bit above that asymptote. And we have -4, 4. And the y-intercept is at 0, 7. Okay. And then dash that in. Okay. And notice the symmetry here. For the last couple here, I haven't been drawing the asymptote in. I can go ahead and I can fill that in for you just to remind you that you are getting that same inverses of one another so that you have that symmetry over y equals x, and I can draw the same thing here over y equals x. Okay. And let's look at the pink graph, look at the end behavior, right? So as x approaches negative infinity, as x is getting really small, y is getting closer and closer to negative infinity, right? So as x approaches 3, so we're saying as x approaches 3, y is approaching negative infinity. And also as x approaches infinity, y approaches infinity. So that's our end behavior. Okay, last thing before we pause, I want to algebraically check that x-intercept. Okay, so let's algebraically check the x-intercept. So verify that algebraically. So I'm just going to, again, turn to the back and we'll verify that algebraically. We're going to let y equal 0, and we'll verify that sure enough that the x-intercept comes out to 7, 0. Okay, so I'll just use the same space that I used to verify the other one algebraically. So we want to get the x-intercept. And the equation is y equals 4 times log base 4 of x minus 3 minus 4. And I'm going to, again, let y equal 0, as we would always do to find an x-intercept. So we'll let y equal 0 equals 4 times log base 4 of x minus 3 minus 4. Now, because of the multiple transformations, we have to do a little bit more algebra here than we had to do in this one up here to find the x-intercept. But the key here is that what we want to do is we want to isolate the log and then change to exponential form, right? So the first thing you're going to need to do is isolate the log. And then we're going to change to exponential form. So let's isolate the log first. So when I say isolate the log, I'm talking about the log plus its argument here. That entire expression we want to isolate, okay? And so what I'm going to do is I'll add 4 to both sides. And that'll give me 4 is equal to 4 times log base 4 of x minus 3. And of course, again, still, if you need to highlight it, this is what we're trying to isolate. So I'm going to divide both sides by 4. So I divide both sides by 4, and I'll get 1 is equal to log base 4 of x minus 3. And now this is the point at which I'm going to change to exponential form, okay? Because I've isolated the log. It's all by itself now, okay? The log and the argument, the value I'm taking the log of. So now we're going to change to exponential form. Okay, so change that to exponential form. Now, typically what I like to do to make things simple is keep the expression that contains the variable on the same side of the equation that it was on. So we'll leave x minus 3 over here. And remember, we're going to be taking the base, which is 4, and raising it to the power that is the log. That's the log is the exponent. So it's 4 to the first power equals x minus 3, right? So 4 to the first power is 4 is equal to x minus 3. Then go ahead and add 3 to both sides to get x. And sure enough, you get 7 is equal to x. And that is exactly what we got when we made our table. We ended up with that same x-intercept. But again, I'm going through this for you because you need to be able to algebraically find the x-intercept as well. Since there is certainly a question and you don't necessarily want to have to graph it, there's a question on your Pearson, and in general, it's good practice transforming from logarithmic to exponential form, okay? So just verify if you go back to that graph, you can see, sure enough, the x-intercept was at 7, 0. So I'm going to say to, keep in mind to note, to verify algebraically. Okay, all right, so we'll take another pause now, and then we'll do the last part of the lesson shortly. Okay, so we are on the last section of the video, example 3, where we're going to calculate inverses of exponential and logarithmic functions. Our goal is to find the inverse of each function. And we're going to use the same process that we have used in the past. Okay, so let's start with part A here. First of all, notice that you're starting with an exponential function, so you know your result has to be a logarithmic function. We're going to be doing the same steps that we've done in the past. So the first thing we're going to do is we're going to notice that we are in function notation. So we're going to want to replace f of x with y. Okay, so let's do that. We'll replace f of x with y. So we'll have y equals 10 to the x plus 1. And then we know the next step is to exchange x and y. Okay, so if we exchange x and y, change their locations, we'll have x is equal to 10 to the y plus 1. Okay. Now, in order to solve for y, we're going to change to logarithmic form. So we're going to solve for y by changing to log form. Okay, and keep in mind we can only do that since the power is already isolated. So you want to make sure your power is isolated, that there's no numbers being added or subtracted to the power. Here you have a number being added within the exponent, but still the power itself is isolated. Okay, so we'll exchange, or we already exchanged x and y, so now we're going to change to logarithmic form. Here we see the base is 10, so we're going to say log base 10. And we know that the log is going to equal the exponent. So we'll put that on the other side of the equation, y plus 1. And the value that the power was equal to, the x, is going to go here. So we'll have log base 10 of x is equal to y plus 1. And remember, whenever you're changing from exponential to logarithmic form, whatever that exponent is going to be isolated on one side of the equation because the log is equal to the exponent. Okay? Now remember, the log base 10 is understood. So 10 is understood. So we're going to want to rewrite that. And when you rewrite that, I'm going to put parentheses around the x. In addition to making that 10 go away because it's understood, I'm going to put parentheses around the x. And the reason for that is because I see that I haven't yet isolated y. And to get y by itself, I need to subtract 1. Okay? So we'll go ahead and we'll subtract 1. And I want to make sure that I recognize that log base x is separate from the minus 1. In other words, the argument of the log is simply x, and the minus 1 would be the k value. In other words, what we have here is we have a base 10 logarithm shifted down 1 from the parent function. This is the k value, not the h value. If that minus 1 was inside parentheses, it would be the h value. So it's important to put those parentheses around that x so that you can distinguish what is the argument of the log and what is not. Okay? And so we'll say equals y. And now I'm going to, in the last step here, I'm going to replace y with f inverse of x. Okay? So I've got the y is going to equal f inverse of x, and that's equal to log of x minus 1. And I could put the f inverse of x on the other side of the equation. It doesn't make any difference. But here's my answer. Okay? Now I want you to notice something that'll help you to check your answers. Notice that the plus 1 was part of the exponent in the original power. Okay? When you have a term such as here, a plus 1, that's part of the exponent in the original exponential function, that number is going to not be part of the argument in the logarithmic function. okay? Because we're doing the opposite operations in the opposite order, okay? So here, if we look at what's happening to the variable here, we're adding 1, and then we're raising that expression 10 to that power. Whereas here, we're doing the opposite operations in the opposite order. So here, first thing we're doing is taking the log, and then we're doing the opposite of adding, we're subtracting 1, all right? So notice that here, the +1 was in the exponent, so pay attention to that. The 1 was in the exponent, and here, the -1 was not part of the argument. Okay, so that's important for you to pay attention to. All right, let's look at part B here. I'm just going to draw this line so we can keep everything separate. Okay, so keep in mind that we're going to use the same steps again. I'm not going to rewrite those steps. We're just going to go through the process. So here we will replace f of x with y. So we've got y equals 3 to the x minus 4. We'll exchange x and y. So we'll have x is equal to 3 to the y minus 4. Now the difference here, though, that we didn't have in the steps over here that you want to kind of keep in mind is that you have to isolate that power. You can't change to log form without isolating that power. So, you know, if you want, you can call this like step 2.5. Between exchanging x and y, before we solve for y, if the power is not by itself, we want to isolate that power. Call it, if you want, step 2.5, we have to isolate the power. Okay? So I'm going to add 4 to both sides, and I'll get x plus 4 equals 3 to the y. Okay, now we can go to step 3, and we can solve for y by changing to logarithmic form. Okay, so remember, the log is equal to the exponent, so leave that exponent by itself on one side of the equation. The base is 3, so we're going to say log base 3, and x plus 4 goes in the middle as the argument. So you've got 3 to the y equals x plus 4. Okay, and of course, I can just change that now, the y back to f inverse of x. So I'll say f inverse of x equals log base 3 of x plus 4. Okay, and something to notice here, you notice here you've got the plus 4 is in the argument, right? So plus 4 here is in the argument. And originally, if we look at the original exponential function, the minus 4 was not in the exponent. Okay, so it's just the reverse of part A. So if you see a number that basically shifts an exponential function up and down, right? It's changing the horizontal asymptote. It's going to change the vertical asymptote of the logarithmic function. You notice here, the horizontal asymptote here is the value of k. It's y is equal to -4. The vertical asymptote here is x is equal to h, x is equal to -4. Okay, all right, let's look at another example here. So you've got f of x is equal to e to the x minus 2, very similar to this situation here. Again, you've got the k value, it's not in the exponent. Let's replace f of x with y. So we've got y is equal to e to the x minus 2. Let's exchange x and y. So we've got x is equal to e to the y minus 2. And I want to, again, I need to do that step 2.5. I need to isolate that power. Okay. So we're going to isolate that power. I'm going to add 2 to both sides. and I'll get x plus 2 is equal to e to the y. Then do step 3, solve for y by changing to logarithmic form, okay? So I've got y by itself, that's equal to the log base e, put that x plus 2 in parentheses, okay? Notice over here, I even put the x in parentheses, even though it was one term, because I wanted to separate that h from the k, okay? It's very important to distinguish whether -1 is an h or a k value, and same thing over here. Notice the difference, right? This part C is like part B, where we have a shift left or right, whereas in part A, we have a shift down. Now, keep in mind that log base E is equivalent to natural log, right? So we're going to say natural log of x plus 2 is equal to y. And then finally, f inverse of x equals natural log of x plus 2. Okay. Make sure if you start with base E that you end with natural log and vice versa. Base E, natural log. Those are inverses. Okay. Some of you, like I said, that's a good review. Some of you in the section 6.3 quiz struggled with that concept that base E and natural log are inverses of one another. Okay. Now, I'm not going to pause right now, but you may want to pause the video and try D, E, and F on your own, and then come back and check and see if you got the same answer as I did. Okay. All right, so let's look at part D now. G of x equals log base 4 of x. Now, I could go through and I could do exchanging x and y, solving for y, but I don't want to even do all that because I want you to keep in mind that we know that if you have simply a parent logarithmic function, which is what we have here, we've got no vertical stretch because the a value is 1, we've got no vertical shrink, we've got no reflection, and we have no shift right or left, up or down. So because of that, I can immediately just say, oh, I know that G inverse of x is equal to 4 to the x. And if you wanted to, you could go through this exact same process we had up here, replace f of x with y, exchange x and y, solve for y by changing to log form, and you would get the exact same result, okay? But I'm just going to go ahead and just leave it at that. Okay. Whenever you don't have a parent log or exponential function, though, you should definitely go through these steps to make sure you're getting the result correct. Okay. So for this one, we don't have a parent. Now pay attention here. Okay. I want you to compare E to F. Notice in E, we have no parentheses. So what you have here is, watch, A times log base B of x minus h plus k. That -2 is not in parentheses here. So the key to keep in mind here is here that h is equal to 0 and k is equal to -2. And so that -2 is not within the argument. So we have to isolate log before we can change to exponential form. And vice versa, compare that to over here. We have a times log base b of x minus h plus k. Here, notice that we don't have a k term. Here, h is equal to 2, k is equal to 0. So here, the log is isolated, so I'll highlight the isolated log. Here, the log is isolated. Here, the log is not isolated, okay? And so you have to isolate the log here. You have to do that step 2.5, where in this case here, it's isolate the log, not isolate the power. So I'll state it as such, right? And of course, here we had to solve for y by changing to log form. Here we're going to solve for y by changing to exponential form. So I think I'll just repeat those steps here to make sure that we're clear on what's going on, right? So we're going to replace f of x with y. We'll exchange x and y. And we will solve for y by changing to exponential form because, see, these are logarithmic equations, whereas up here we had exponential equations. And then, of course, replace y with f inverse of x, or, you know, in this case, it's going to be h inverse of x, right? All right, so first step, replace f of x with y. Okay, so h of x will become y equals log base 7 of x minus 2. We're going to exchange x and y. So we'll have x is equal to log base 7 of y minus 2. Now here's that step 2.5, right? Because we've got that log base 7 of y that we need to isolate, because that minus 2 is not in the argument. So we have to get the log by itself, right? So we're going to do that step 2.5 here. We'll call it isolate the log this time. Okay, so it's very important that you don't skip that step. So we'll isolate the log by adding 2 to both sides. And we'll get x plus 2 equals log base 7 of y. And we're now going to change to exponential form in order to solve for y. That's the step 3, right? So remember, the base is 7, the log is equal to the exponent. So base is 7, the log is equal to the exponent, and that's going to equal y, okay? And then I can just rewrite this. Remember, this is h inverse, so h inverse of x is equal to 7 to the x plus 2. Okay? And then last one like this, and then we'll just do a short word problem. Not really a word problem, but just an application where we use this for a formula, finding the inverse using a formula. Okay. So for this one, remember what we talked about, the difference between e and f. Not only is the base different, here we're log base 7, here we're log base e, natural log, but also here the minus 2 is within the argument, and here the minus 2 is not. Here the minus 2 represents h is equal to 2. Here the minus 2 represents k is equal to negative 2. Okay, so that's important for you to see that difference. So we're going to replace j of x with y. So if that y is equal to the natural log of x minus 2, we'll then exchange x and y. So we'll have x is equal to the natural log of y minus 2. And keep in mind that before we change this to exponential form, because that would be the next step, keep in mind that natural log is log base e understood. So we have x equals log base e of y minus 2. Remember, that is understood. And it's useful to write it in that form to get the exponential equation right. The log is equal to the exponent. So the base is e. So we have e to the x is equal to y minus 2. Okay? Now, in order to solve for y, of course, at this point, we need to add 2 to both sides. Okay? So you notice up here, we didn't have to isolate the log. The log was already isolated. And at the end, we have to isolate the power. And it's just the opposite here. Here we had to isolate the log at the beginning. And then at the end, once we changed to logarithmic to exponential form, the power was already isolated. And so I'm going to add 2 to both sides. And I'll have y equals e to the x plus 2. Okay, make sure pay attention to where that plus 2 is going. It's a k value. Okay, just like minus 2 was an h value, the minus 2 is within that argument. The plus 2 is not within the power. It's not within the exponent. So pay attention to where that plus 2 is. Don't write it as a superscript. It's at the same level as the base e. So now rewrite y as j inverse of x. So j inverse of x is equal to e to the x plus 2. Or excuse me, see, even I'm doing it here. So just be very careful. So e to the x, and then that plus 2 is a k value. So just catch yourself there. Okay? All right, last but not least, we're going to look at example 4, and we're going to see how we can use inverses of logarithmic and exponential functions to apply to a real-world situation where we're going to interpret the inverse of a formula involving logarithms. Okay? A company uses this function to relate sales revenue R and advertising costs A. Okay, so what we're saying here is the sales revenue depends on the advertising costs. Okay, and you haven't probably been involved necessarily in a business yet, but maybe your parent has. And generally, you probably we would hope that what happens is as you increase your advertising costs, then hopefully your sales revenue, how much money you make on your goods that you sell, will go up as well. So as A gets larger, R should get larger, right? So R is the revenue in thousands of dollars. A is the advertising costs in thousands of dollars, okay? And we want to know what is the equation of the inverse formula, okay? So we're going to do mostly the same steps that we did with just ordinary finding the inverse. But the one thing that we're going to do differently is that we're not going to exchange the variables, okay? And I'm going to make a note of that over here. So to find the inverse of a formula, do not exchange variables. Okay, and that's because they have specific meaning, right? So R means revenue and A means advertising costs. So we can't just change their location arbitrarily. Okay, so since they have specific meaning. Okay, so what we're going to do in this case, we're just going to solve for A in terms of R. Okay, that's what we're going to do to find the inverse formula. Okay, so I'm going to use the same colors that I've got here. I'm going to use green for the R, and I think this is red, but we'll use pink for A. All right. So we'll write. I'll rewrite the formula here. R is equal to 12 times the log of A plus 1 plus 25. Okay. Now, in order to solve for A, what I need to do is isolate the log and then change to exponential form. So basically, we're doing, very, very similar to what we did up here. We don't have to worry about replacing f of x with y because it's not in function notation, and we're not going to exchange x and y. So basically here, we're going to go right here to the third step, okay? We're going to solve for A by changing to exponential form, but the first thing we have to do is we need to isolate the log, okay? So we're going to isolate the log, and then we're going to change to exponential form. Okay, so to isolate the log, we will subtract 25 from both sides of the equation. Start with that. And so we'll have R minus 25 equals 12 times the log of A plus 1. Okay. Now I want to try to get, I need to isolate the log. So what I'm saying when I isolate the log, I'm taking the log with its argument, okay? With the value in parentheses, with the horizontal shift, okay? So I'm going to divide by 12 on both sides of the equation. And I'll write R minus 25 over 12 equals, now the 12s are going to cancel out, log of a plus 1. Okay, so now I've isolated the log. Now I can change to exponential form. Okay, now keep in mind, I have base 10 is understood. So I'm going to rewrite this now with base 10. So I've got r minus 25 over 12 equals log base 10 of a plus 1, right? And that's understood. That base 10 is understood, okay? Now we can change to exponential form. So the base is 10, r minus 25 over 12, that entire fraction is the exponent. And that's going to equal a plus 1, okay? So we've got 10 to the r minus 25 over 12 is equal to a plus 1, a plus 1, okay? And now the last step to get a isolated, of course, is to simply subtract 1, okay? So I'm going to subtract 1 from both sides of the equation, and I'll have a by itself, okay? So a is going to equal 10 to the r minus 25 over 12 minus 1, and make sure you put that minus 1 at the same height as the 10. That is not part of the exponent, okay? So that is the equation of the inverse formula. And you could, of course, put the a on the left and the exponential expression on the right. So it says, what is the equation of the inverse formula? Here's the equation of the inverse formula, okay? Now, finally, it says which equation would be easier to use to find a value of a for a particular value of r. And basically, we're saying, given r, would it be easier to use the original equation or our new equation? And I think, obviously, we'd all say, if we're given r, it makes sense to use the inverse formula. And that's the reason that we want to solve for a in terms of r, right? So we can say, obviously, the inverse would be easier to use to find a for a particular value of r. Okay? And pay attention to this last problem here, because there are questions on your Pearson Realize that address a very, very similar question. All right? And that'll do it. That I did this video pausing a couple of times to remind you to pause, to go back, review information, make sure you're completing your note guide so you have the notes, okay? And as you know, there are 2 assignments related to this. One is your Pearson Realize assignment, and one is just a short worksheet with 4 graphs on it that you need to complete, where you have to graph the log function as well as dash the inverse, the exponential function, and that'll be due on the same day as the Pearson assignment. Okay? Have a good day.